Hello, I'm back with another lesson on calculus, this time finding turning points and classifying them. Why don't we get started? In order to find turning points, you need to be able to differentiate. So, let's differentiate the following. For number 1, we have y equals 3x squared minus 9x plus 1,234. To differentiate, you bring down the exponent and multiply out front. So 2 times 3 is 6. And then take away 1 from the exponent, okay, which results in 6x. When you have 1 as your exponent, you simply bring down the coefficient of x. And anything without involving an x will drop off. So we have 6x minus 9. For number 2, again, we bring down the front. So we have 3x and take away 1 from the exponent, so we have 3x squared minus 2 times 4.5 is 9, so we have minus 9x plus 1,234. The x drops off. Any constant, when differentiated, just disappears. The result is 3x squared minus 9x plus 1,234. Notice the derivative of number 2 is the exact same as the function in number 1. That's called the first derivative. So, if we derive it again, that is called the second derivative. You can actually do the derivative more than once. So we have the first derivative and the second derivative, just for informational purposes. Let's go on to the turning points lesson. Okay. Here is our function. Our function has 2 different turns, okay? The question I have for you is, where on the function do we have a positive value for the gradient? Remember, a positive gradient goes from bottom left to top right. A positive gradient. So as you can see, leading up to leading up to A, we have a positive gradient the whole way. Okay? Leading up to A. Also, if you look at the end after B we also have positive gradients. We say that the function is increasing at these points. It's increasing because it has a positive gradient. Where on the function do we have a negative values for the gradient? Our negative gradient is from top left to bottom right. If you look in between A and B, the gradient is always negative. So the function is decreasing. Okay? Question 3 is, where on the function do we have a gradient of 0? Well, a gradient of 0 is a horizontal line. So if you look at point A and you look at point B, we have a horizontal gradient, so the function has a gradient of 0. Notice, when we go from a positive value for the gradient, and then we have a gradient of 0, and we have a negative value for the gradient, we have a maximum point up here. And when we go the other way, we have a minimum point. Okay? So, the turning points, we call them turning points. They occur when the gradient is equal to 0. What we say is the point A is a maximum, a local maximum, because we're going from a positive gradient to a negative gradient. At point B, we have a local minimum, because we're going from a negative gradient to a positive gradient, when we're moving from left to right. It's decreasing, then increasing. Where is the absolute minimum on this curve? We've restricted the curve. The curve is restricted. Where is the absolute minimum on this curve? That's right. The absolute minimum is at point C. Okay? The absolute minimum is at point C. Where's the absolute maximum on this curve? Well, since the curve is restricted, the absolute maximum is going to occur at A. Okay? So we talk about maximums and minimums, and we also talk about turning points. Now on to our activity. What I'd like you to do now is participate in this activity. Here is a quadratic curve. Okay? The quadratic curve does have a turning point. In this case, it's going to be a minimum. I've drawn it for you here. We're going to find this minimum in two different ways. In the past, you would have seen completing the square before differentiation. So we're going to find the minimum by completing the square. Let's have a look. So here's the curve. To complete the square, we only worry about the first two terms in the quadratic, x squared plus 2x. We're going to complete the square on these two terms. In order to do that, we have to make the square. To make the square, we take the term in front, we take the coefficient of x and we divide it by 2. That is how you make the square. Okay? However, once we make the square, we've got a little bit too much. What we have here is 1 squared too much. So to complete the square, we have to subtract 1. X squared plus 2x is equal to x plus 1 all squared minus 1. The 3 is still hanging around here, the minus 3. So let's just bring that along for the ride. Now we simply just add these two together, and we get x squared plus 1 squared minus 4. This is the same as our original function. The turning point is located at 1 unit to the left and 4 units down. If you recall, the completed square version gives us sometimes this is called the vertex form, and this gives us the vertex at minus 1, minus 4. So let's go back. The other way we're going to find this turning point is by differentiation. Okay, let's see which one you think is easier, which one you like the best. Let's do it by differentiation. Here's the curve. Okay? The first step to find the turning point is to differentiate. So the derivative of x squared plus 2x minus 3 is 2x plus 2. What we want is we want the x-coordinate that gives us a gradient of 0. So if we set our gradient equal to 0, we will find the x-coordinate where this occurs. So 2x plus 2 equals 0. Rearranging and solving gives x equals minus 1. 2 times minus 1 is minus 2, plus 2 is 0. To find the y-coordinate, we have to substitute our value back into the original function. Our original function generates points. So we simply substitute minus 1 back into the original function, do the math, and the result that we will get is minus 4. This agrees with what we just did. This agrees with our completed the square term. It's the same point. Which one do you like best? I'll let you decide. For me, I think this is much more powerful. Let's go back. Now's the time to pause the video and do the exercise. Feel free to try this exercise. See if you can find the turning point using calculus. Okay, welcome back. And here's the answer. Okay, well, I hope this was informative. Remember, in order to find the turning points, you take the derivative of your function, you set it equal to 0, solve for x. That gives you the x-coordinate of your turning point. Substitute x back into the original function, and that will generate the y-coordinate of your turning point. This is true of almost all functions involving polynomials. Okay? Thank you for watching my video. Goodbye.